Hey everybody, welcome to ARE Live. I'm Mark Tier, the founder of Black Spectacles, and today I'm with Mike Newman, who is going to review the Building Design and Construction Systems exam. Tonight, Mike is going to help you understand sort of the big concepts that the questions are really going to be asking. Because while there's lots of different sort of places the exam could go, the main topics cover things like keeping water out of a building, keeping things from falling down, durability and maintenance, and thermal considerations. And also, if you're looking for exams that sort of overlap a little bit, the building systems and the construction documents and service exams cover similar topics like construction and detailing, as well as organizing a set of drawings. So that's sort of what's on tap in today's episode. But before we get started, if you'd like to attend our next ARE Live broadcast, which is on the schematic design exam, visit blackspectacles.com/podcast to register. You can see it here right now. So if you just click the little registration button here on the podcast page, you can register. During the broadcast, you'll have a chance, just like today, to ask questions and share your answers with Mike. And of course, if you don't know Mike, he's an adjunct professor at the School of the Art Institute of Chicago. He's also the founder of Shed Studio, and he is the instructor for Black Spectacles' online AIA ARE prep curriculum. And if you haven't already checked out our AIA ARE prep curriculum, head over to blackspectacles.com to watch any of the free tutorials from the courses. And today we have a special Black Spectacles promo code to share, so make sure you stick around until the end of today's episode. But first, let's hand it over to Mike.
Okay. Thanks, Mark. Today, as Mark said, we have the Building Design and Construction Systems topic. This exam can go anywhere from really large-scale decision-making to quite fine-grained detailing. The essence of this, though, is, as Mark said, you're using that fine-grained detailing, those other kinds of questions, as a way to think about the big issues of how does a building stay dry, how does it stay warm or cool, how does it stay comfortable, how does it not fall down, all of those kinds of basic issues. And so we're going to, on this particular version of the review, we're going to use a lot of that fine-grained discussion because we're only going to run through a few topics. So we're going to focus on this one, on these fine-grained detailing materiality issues. But remember that as we talk about them, what we're really talking about are these bigger scale issues. So we're going to talk about soils, concrete, masonry, wood, a bunch of that kind of stuff in order to kind of really think about these kind of big scale decision making for buildings. And so we're going to be at small scale and big scale all at the same time. So remember, as we talk about these things, there are also a whole lot of other potential topics that the exam can go to, and we'll pick up another one of these events down the road where we pick up some of those other issues. But hey, we got to start somewhere. So we're starting here. Let's start with question number 1. So I'm just going to dive right in. Hope everybody's ready. Question number 1, which of the following is not true regarding bentonite waterproofing? Okay, A, it is made with volcanic clays. B, it swells to a watertight barrier. C, it can be installed on top of a mud slab in a crawl space. D, it can be installed in hydrostatic condition. So first thing we need to think about with a question like this is, first of all, kind of what the heck is actually going on? What we're really talking about when we say bentonite waterproofing, bentonite is a type of clay. So it's actually, when it's dry, it's a very dusty, it's like a bag of very dry, dusty clay. And what's really amazing about bentonite is that when it gets wet, it actually gets larger. So, okay, why is that interesting to us? Well, if we have, let's say, a concrete wall, and that concrete wall has a seam in it or a crack in it or something, and we can fill that seam or crack with the bentonite, and then other layers of stuff is added on, like let's say we have boards of insulation over the top or something. There's something that kind of makes it all a contained situation. If we have that bentonite in that crack, if water does get to that crack, which of course water will, right? Because water will always find its way into whatever crack there is, because that's the nature of water. When the water gets in there, it'll make that bentonite wet. It then expands, and when it expands, it presses against the sides of the crack that it's in, and it becomes waterproof. It becomes a way of stopping the water from getting through. It's kind of this amazing, low-tech, simple system. But it has a number of drawbacks. And the biggest drawback it has is that if it's in a situation like, say, for example, C, which would be the answer, where I have a mud slab. So I have a simple slab. For those of you who don't know the term mud slab, it's used in things like crawl spaces or places where you don't really need a full concrete slab, but you take some Portland cement, you mix it in with some water and some of the local soil that's right there, and you make a kind of a very rough-hewn version of a concrete slab. So it's not particularly strong, not particularly useful, but it's very, very cheap and easy and gives you kind of a hard, simple surface that you can kind of, use for construction purposes and things like that. You wouldn't really want to live on a mud slab, but it kind of makes it sort of workable. But if I had that mud slab in that basement and I then put the bentonite on top of it as a way to hope that I was going to get waterproofing out of it, well, if I had water flowing onto this space, as the water would flow in, it would just take the bentonite with it, because the bentonite needs to be in a contained space for it to work. So they're very different animals in these kinds of different situations. A contained space where water is moving through capillary action and surface tension and those kinds of things, that containedness is actually what's going to make bentonite work. In an uncontained situation, I would need something that's more like a membrane. So in this situation, I might use something similar to a fluid applied waterproofing, or I might use an actual like visqueen membrane, or I might use kind of similar to roofing materials. There's a whole bunch of ways I might try to get something to be waterproof in something like a mud slab or a slab, but bentonite would not be the answer. So bentonite, amazing, interesting material in terms of how it can keep water out because it's low tech and cheap, not terribly cheap, but cheap enough, and has zero toxic aspects to it, but only works in certain scenarios. So again, thinking about this is a detail kind of question, but what we're really trying to make sure that you understand, or what the exam would be trying to ask you really here is, do you kind of get that water works in different ways and that there are going to be different ways of attacking it? Right? That not every waterproofing system is equal in terms of how it works and how it would be used, and so you have to find the right one for the right fit. So, hope that made sense. Let's move on to number 2.
Yeah, and before we do,
yes.
It looks like Devon, Dustin, Judd, Kevin, Michael got this right. A couple of folks thought that maybe it was B or D, swelling to a watertight barrier, or the other one?
And that's because people would assume B because it sounds so crazy that it actually works. Like, not all clay will work. Bentonite is really the only type of clay, actually it's the only one I know of, maybe there's others, but typical clay wouldn't do this. But it's this kind of amazing thing. It swells quite a lot when it gets wet. It really is expansive, and it does it so fast that it actually, when it gets wet, it swells and fills the crack, and therefore makes it watertight. And then as it dries out, it goes back to being a sort of drier, dustier material, but that's okay because there's no water, and there's no water because it dried out. And then when it gets wet again, it swells again, right? Which is why you can't have it be in a situation where it can get washed away. All right, let's move on to number 2. So, okay, hopefully you noticed, if you were doing this little mini exam at home, hopefully you noticed that I was actually kind of being a little tricky here. So the question is, number 2, what is the nominal dimension of a CMU block? First thing we have to think about is, all right, CMU block, that's a concrete masonry unit. That's like a really standard concrete block. So let's see if I can do a quick version of it here. It was a terrible version. All right, very exciting. Right, so there's our concrete block. And one of those blocks, there are probably, 30 or 40 different versions of standard block sizes. But having said that, probably 80% of the block that gets used is this one very simple type of block. It's used all the time, and a vast majority of the situations. And in this situation, this is actually 16 inches by 8 inches by 8 inches. So it's a 16 by 8 by 8 would be the answer, or 8 by 8 by 16. And the tricky thing that I did here is I actually asked you for nominal dimensions, and generally in a question like this, people would be really asking for the actual dimensions. Because there's a difference between nominal and actual. The nominal, it means the named dimension. This is what we call it. We call it a 16 by 8. And so that's a useful, important number, and it actually is that when you include the mortar beds. The actual numbers here would be, usually it's about a 3/8 of an inch mortar bed, so it would be 15 and 5/8, and 7 and 5/8, and 7 and 5/8. And those would be inches. So if I had actually asked, instead of nominal, if I had asked actual, you would answer it 7 and 5/8 by 7 and 5/8 by 15 and 5/8. So this system is a way of, sort of very simple way of having a two-handed process where I butter it with the mortar, I have the two hands, I lift it up, I place it into place. 3 of these in a row, 16, 16, and 16, is going to get me 48 inches. 48 inches obviously is tied into all the other modular dimensions that happen on job sites. So 16-inch stud spacing, 24-inch stud spacing, 4 by 8 sheets of plywood, all of those things, they're all on the same basic module. This is in the United States. In other places, everything gets different, although you'll find similar issues, similar ways of being modular. So this system allows you to, without really even thinking about it, tie, like if you know that it's 4 sheets of plywood wide, you can then figure out very quickly how many blocks those are, how many CMU blocks those are. The advantage of the CMU block is there's all sorts of advantages. It's a very strong material. It has all the holes in it. Why does it have holes? Well, it has holes so you don't have to carry a giant chunk of concrete. So it's making it lighter in terms of placing it. It also allows you to put rebar going through so that things can be tied together. Each of the different courses can be tied together. All of those things they're all modular enough that across a whole wide range of uses, these things can be used in any one of those ways. So it can be without rebar, it can be with rebar, it can be filled grout into the center, it can be not filled grout, just a dry sets. There's a whole series of different ways it can be used, but by the simplicity of it, the sort of nature of everybody understanding exactly what they're getting, it's very simple setup. How big the holes are, therefore how light the block is, there's a lot of range of that, but the basic idea will hold true on a whole lot of these. Then you can also get into specialty ones that are 4 inches or 6 inches or 4 inches tall. There's a big range of other possibilities. But like I said, the vast majority of them fall right into this category. All right, I'm going to jump to number 3, which is related. Well, similar. So number 3, what is the nominal dimension of an 8-foot 2x6? Again, this was the same sort of tricky thing. Almost everybody would be assuming I would be asking what is the actual dimension, and I did this in order to make the point that you have to actually be really careful about how you're reading it. Don't make assumptions. Actually read all the words and really parse them as you move through it quickly, but you have to parse them as you move through it. So the key thing here is the nominal, what is the nominal dimension of an 8-foot 2x6? And so the actual answer to that would be 8 foot and 2 and 6. So that's the named thing. That's what that is. That's an 8-foot 2x6. If I had asked for the actual dimensions, then what we'd be talking about is a smaller size than the 2 and 6. So if this was, say, a 2x4, that actual dimension would be 1.5 by 3.5. Probably many of you know this, but we'll just run through it real quickly. If that was a 2x6, like we were talking about here, that would be 1.5 by 5.5. If that's a 2x8, this is the tricky part. It goes to 1.5 by 7.25. And then all the other ones after that, the 10s and the 12s, would all go to 9.25 and 11.25. So if we're similar thing, this is all with dimensional lumber. So this is a similar thing as 4x4s, 4x6s, 2x4s, 2x12s, all of that kind of stuff. That's dimensional lumber and it's dressed lumber. So in our situation, if this question had actually asked what is the actual dimension of an 8-foot 2x6, it would be 1.5 by 5.5, and then here's the kind of odd part, 8 foot, right? Because it's smaller in all of the dimensions, but not in the length dimension, because that doesn't make any sense, right? You're the one who's cutting it at 8 feet. The other dimensions are smaller because that's a dressed dimension of the wood. There's kind of an interesting history to all this stuff. If you've worked on older buildings, you may well find that you've actually worked in spaces where you had actual 2x4s, where it was the actual dimensions of a 2x4, like 2 inches by 4 inches. And then over the years, they got sort of smaller and smaller. And the way that most people talk about it is that they would cut it actually as a 2x4, and then by partly it shrinks in the kiln process or the drying process, and partly it shrinks when they plane down the edges. It's called dressing the edges. And so each of the edges gets planed down a bit, and so it starts at 2 inches and goes down to 1.5, and it starts at 6 inches and it goes down to 5.5. In actuality, that's not even really true anymore. It actually starts at about 1 3/4 or something like that, and then 5 3/4, and then gets planed down from there. And the realization happened many, many years ago that you really didn't need the full 2 inches. When you're doing something like platform construction or just any kind of framing with 2x material, it became obvious that because you have so many pieces of framing every 16 inches typically, that having a full 2 inches of wood just wasn't really necessary. That wasn't, you're not using the wood as a big, solid, robust material. You're using it more like a whole series of toothpicks that all get lined up, and because there's a whole lot of them, it doesn't really, they kind of do the job. They carry the load. And so it's been engineered down over time to be these very thin 1.5 inch wide members, and that's really plenty big enough. So it's kind of an interesting way to get at it, this idea of the nominal and the actual. You should be really careful. This is such a simple thing to know. Please don't make a mistake on this, because it's such an easy way to miss a question, and there's really no reason to. But you can see how it ties into all of these other issues. There's sort of historical aspects to it. There are ideas of the specific spacing starts becoming an interesting question. Like you start saying that something is on 16 inches on center. That doesn't mean that there's 14 inches of space in between. That means there's 14.5 inches of space in between. So kind of understanding those numbers, you start seeing whole walls very, very quickly, and it adds up to a whole sort of assembly system.
We do have one question here from Ben.
Yep.
And he's asking, does NCARB expect the answer to follow a convention about the order? In other words,
no.
Length times width times
that's
WWD.
That's a really good question. I don't think they would. Typically, it would actually be. I did it kind of backwards on that first one where I put 8 foot and then a 2x6. Really should be 2x6 by 8. But you'll actually see it done differently. It depends on who you're talking to. Like if you go to Home Depot, they'll do it one way. If you go to some other places, they'll do it another way. It doesn't really matter that much. I don't think it would matter. Like they won't give you the same numbers, but in reverse order or anything like that on this kind of thing. And actually, I don't think they would technically ask you this exact question. It's more, this is a question that kind of gets at all of these different kinds of issues. And one other quick thing to say about this, just in general, you may, I don't know if you notice, but when I'm doing this, I actually should have inch marks on when I say 1.5 inch by 5.5 inch, and then the foot mark at the 8. But I do not have it when I'm talking about the 2x6. Right? There's no inch marks on the 2 and the 6, and that's because it's not 2 inches by 6 inches. It's just that 2x6 is the name. It's like you're giving it a name, and if I put the inch marks, then what that's saying is it is actually 2 inches by 6 inches. All right, that was a good question. Let's move on to the next one. All right, number 4. You are estimating how many bricks you will need to order for a 48-inch wide double width wall that is 32 inches tall. I have wall in there probably too many times. For part of a patio design. The bricks are sort of standard bricks and normal bricks. How many bricks would you need in order to do this? So, okay. A couple things to talk about here. One is sort of stacking bricks. If we look at a quick section of a portion of the bricks, if I have let's say 3 bricks stacked on top of each other, and then I have another 3 bricks stacked on top of each other next to them. Each one of these lines is considered a course of brick. Each one of these lines is considered a width of brick. I've talked to people a bunch of times. Some people say width, some people say width. I prefer to say width just because it differentiates it from the word width. But I think width is actually the technically correct term. So people will say it different ways. It doesn't really matter. But that's the vertical line is a width. The horizontal is a course. And every 3 bricks in a kind of standard normal run of bricks is 8 inches. So when you stack them together with their mortar beds, that's an 8-inch height. So we start thinking about this wall that we talked about. Okay, here's our wall. And it's 2 widths. And this is 32 tall, and this is 48 long. So what do we know about brick? Well, one of the things we know about brick, a typical brick, is that typical brick is 8 inches by 4 inches. And the height is sort of the odd, right? Because the height is like 1/3 of the 8 inches. So most people don't really worry about the height. They think of it in the groupings of 3 because it's just easier to do the calculations. Now remember, just like the CMU, that means that the 8 is actually 7.5, 7 5/8, a couple of them, like there's quite a range in there. Bricks are more malleable than CMU, so there'll be a little bit more of a range, but it'll be a similar thing. But in terms of nominal dimensions, it'll be 8 by 4, 4 by 8. So that 8 inches in that brick, I start looking at that 48-inch length of the wall. I can have every one of the bricks is 8. That means I have 6 bricks in that row in that course, every part of section of that wall, every course of that wall. And then now the question is, well, how many courses do I have? Well, if I have 32 inches tall and every 8 inches is 3 courses, so I can start dividing that into 4 groupings. 4 groupings of 8 inches. So I've got 4 groupings of 3 courses each. Therefore, that's 12. 4 times 3 is 12. So I have 12 times 6 is going to be equal to 72. So as I did when I was first writing this, I was like, okay, so the answer is A, 72. And then I realized, oh, I tricked myself. It's a double width wall, so I have to double it because I have the same number of bricks on the back side of the wall as well. So the actual answer here is B, 144. So this is one of those things, you start seeing a few simple dimensions and suddenly it all starts piling together. Like one of the things you probably should have noticed if you didn't realize already is the stack of 3 bricks, 8 inches, that's the same as a CMU. So same as the height of a CMU. So I can say if I have a backup wall of CMU with an air gap and then a veneer of brick, I can say that every 3 bricks is 1 CMU, every 3 CMUs is going to be 9 bricks, right? You can very easily sort of run these things back and forth, and that's really important because you also want to be able to make sure that, if I have 3 bricks in a row, and then I have a CMU back here, and I've got an air gap, I want to be able to put the ties, the ladder ties, or some other kind of ties across. I want to know that those are always going to match up with each other, so you're not having a sloped tie or something. So the fact that these things are actually modular is really useful and helpful. And once you start getting into just a few of those dimensions, they suddenly all start to kind of tie together, and you start seeing how everything kind of fits together. And it's actually a very useful way of thinking about these things. Another little tricky thing that I threw in here was a square of bricks. Square is actually not used for bricks. That's used for roofing. So you'll often hear people who refer to a square of roofing, and what they're talking about there is a 10 by 10, 10 foot by 10 foot area of roofing. So if you have a shingle that would be exposed, would be say 1 square foot exposed, then there would be 100 square, like whatever it would take to get 100 square feet of exposed finished asphalt asphalt shingles, or slate shingles or whatever. This is a way of talking about kind of ordering roofing materials, because they are so different in terms of how much they overlap and all of that. What you really care about is what is the finish amount that I'm going to get. So a square you'll see show up, but not about brick. It'd be about roofing. A couple of other things to mention here, that when you're tying these things together, when you start thinking about how all this stuff kind of fits together, you'll notice that the bricks are much more, they fit into the module, but they're also much more malleable. The thickness of the bed can be adjusted. You can have a thicker mortar bed, you can have a thinner mortar bed. So you have a lot of ability at sort of adjusting something to get it right. But the thing you'll definitely find is that this dimension, that 8-inch dimension, will show up all over the place, because while getting the heights to sort of adjust easily, you really don't want to get into situations where just sort of by accident of not really thinking it through, I have like a sliver of brick next to a full brick. Like that starts looking really ugly. And so using the module in that direction becomes really important. And then one last thing to mention, when I did the 48 inches wide on the base of this wall and said, well, we just divide that by the 8 inches to get 6, and that's our number, we all know that most of the time this is going to be a running bond. So a running bond is going to be something where I've got a brick lined up, and then the next one up or down would be a half a brick, and then this is on the half lap, right, et cetera, et cetera. But with the 48 inches, this half brick is going to be matched by one at the other end, and so it's still going to be the same number. It's still going to be 6 bricks across. I'm just cutting one of them in half and using the 2 halves on the ends.
We do have a question here from Rajane. She's asking, how do we run a course for a double wythe? How are the ties?
That's a really good question. It actually is kind of complicated because it depends on what the wall is. Often if you're just doing like a patio wall or something where there's not a lot of loading on it and it's not acting as a retaining wall, yeah, you kind of don't really worry about it too much, and maybe you have ties every once in a while just to sort of tie it together, or every once in a while you do one brick, because remember they're 4 inches wide nominally, and that 2 of them together is equal to an 8-inch length of a brick, that you do a header going the opposite direction, and it ties the 2 withes together. That's how the old school folks did it. That's why you would see those patterns with like a common bond or a Flemish bond or something often has the end of the brick shown. It's because they were tying more than one withe together as a way to make the different withes work bondedly together in a very strong structural wall. In something like an outdoor wall, you might do that a few times just to kind of tie everything together. That's probably better in an outdoor wall and like a patio wall than using a metal tie, because those walls are going to get very wet. They're going to have water coming from both sides, and so they're going to get saturated a lot. And you're just asking for trouble of corrosion and stuff on the metal ties in the wall from that standpoint. Kind of interestingly, just on that point, people think of brick as being kind of waterproof, but it's not at all. It actually is very, very, very porous. And so when you get a heavy rain, that rain will just soak right into the brick and go right all the way through it, and then eventually breathe back out and evaporate back out to the outside. This is the whole reason why you have cavity walls most of the time, or these days we have a veneer, one single withe of brick on the outside, and then an inch or 2 of air gap, and then a CMU backup or other brick or wood, or wood studs or metal studs or whatever the backup structural wall is. And that withe of that veneer, that front withe of brick, is really just acting as kind of like a rain screen. It's just allowing to sort of shed the water mostly. It absorbs quite a bit of the water. It evaporates back away. Any of the water that does get through that brick falls down the back side of that front veneer of the brick, and then you have weep holes to allow it to get out. So that absorption of the brick is really pretty amazing and massive. So you don't want to do much unless it's a very well protected wall with metal, unless it really is important structurally. So tying them together in this situation, I'd probably use the headers going from one width to the other. If it was more of a retaining wall where there's actually high soil on one side and not on the other, then I'm probably actually going to have rebar, and I'm going to have holes in the brick, and I'm going to have rebar going through it in order to give it more of a capacity as a full structural wall. Probably, if I was really being smart about it, if I was using it as a retaining wall, I would actually do a concrete retaining wall and then just do a facing of brick on the outside, because the concrete's so much easier to use with the rebar. Hope that answered the question.
Yep, looks good. Looks like everybody got that one right too. So
cool. All right. This one is dead simple, but easy to make mistakes on. And this is actually pretty much a direct run from the vignette. So this is a way of kind of touching on the vignette for the building design and construction systems, which is a couple different vignettes, but one of them has a stair design in it. So, okay, on this one, our situation here is we have to figure out the number of risers. The stairwell goes from the 0-0 elevation up to the 8'10" elevation where there's a door, and then it continues up to the 13'6" elevation where there's another door. So our first consideration is going to be from 0-0 up to 8'10". So we start thinking about, all right, we have a full run of 8'10". That's going to be the equivalent of, let's see, 8 times 12 would be 96. Plus 10, so that's a vertical run of 106 inches. So our total vertical rise from the ground floor up to this level is 106 inches. So the first thing we're going to do is we're going to say, what's 106 divided by 7? And why 7? Because in a public stair, and this is a library, so it's a public building, in a public stair, for accessibility reasons, the highest riser we are allowed is a 7-inch riser. If we're in a single-family house or in a mechanical space or some various other specific situations, I can actually have a higher riser. It depends on the municipality. For single-family houses, where I am, I can do it up to, I think, an 8-inch riser. Some places actually can go up even a little higher. But in any public stair, 7 inches is the maximum riser. So our first hope is that if we divide 106 by 7, we'll get a nice even number. As it turns out, we do that, and I believe we end up with 15.14. So that means we have 15.14 risers. Well, obviously there's a little problem there. You can't have 0.14 riser, because if you do, it's like a little sliver of a riser. It's going to be a trip hazard. People would fall all over the place, which clearly is a problem. So what that means is we're going to actually round up. You're always going to round up to 16 risers in this case. And why you're rounding up? Because if we round down, that means that little bit extra is actually going to become, it's going to make it so that each of those risers were, 7 and a 16th or 7 and an 8th. And we just said 7 is the maximum riser height you can have in a public stair. So you have to round up. That's a mistake that people make all the time, because it sure seems like you should be able to go to 15 when you're so close to it on this scenario. So in this case, if we actually went back in and we divided 106 by 16, I forget the exact, but I believe it comes out to 6 5/8 inches. So that means each riser we have 16 risers at 6 5/8 each. Yeah, 6.625, 6 5/8. So that gives you kind of a clearer sense. We have 16 risers for that first part. They're each 6 5/8 inches. Now we have to think about this second run of stairs. So we have a second run. We have 13.6. That's going to be equivalent to, let's see, what is it, 156 plus 6, which is going to be 162 inches total from the 0 up to the landing, but we don't care about that whole thing. We only care from the 810 up to that. So we take the 162 and we subtract, what was the number, 106, and that's going to be equal to 56 vertical inches from landing 1 up to landing 2. We divide 56 by 7 on the hopes that it's going to work out nice and evenly, and we get 8, and sure enough it does. So in this situation, we're going to have 8 risers at 7 inches each. So in total, we have 16 plus 8, we got 24 risers. So A is the correct answer. Intriguingly, some people get sort of screwed up by the fact that there are different riser heights on the 2 runs of stairs. That's just the nature of the fact that the heights are set by some other reason. Like there's a reason why we're coming to this height, and there's a reason why we're coming to that height. In this case, there's no way we could have them all be matching risers. But it is important that the risers are all the same from here all the way up to there, and then a different same, but all the same from there all the way up to there. You can't have a riser height change in mid-flight. You shouldn't, even if you have a mid-landing, there's no reason why one flight up to the landing should be different than the other flight. The reason that this one it does is because there's a door at that landing. That landing is a set location. It's not just halfway between the 2 floors you're trying to get to. So the answer is 24, 16 plus 8, but kind of realizing that there's this very simple thing. You start by dividing it by 7 just to get the ballpark, then you round up. If you have to, which most of the time you will have to, it's pretty rare that you end up with a nice even number. And then you go back and divide it by whatever that number is again, and now you actually have both the number of risers and the riser height very simply. I've made it look kind of complicated here. You start to be able to do this in your sleep if you haven't already been able to do it.
Okay, I think everybody got this right here. Rich asked a question.
Yep.
Technically, riser height from 0 foot 0 to the first landing can be different than from first landing up to 8 foot 10, right?
So that's actually a little bit of a complicated question, even though it seems simple. Technically, that could be true, but pretty much any code official that if there wasn't a reason why that mid landing on that first run from 0 up to the 810, that the part way up, if there wasn't a reason why it was placed where it was, like there's a door or an access panel, or there's some reason that would place that, then most code officials would say, no, you got to make them all the same. Because you're always trying to make them match as much as you possibly can. Now, if you're working in an older building, there's a lot more leeway, because sometimes you're working with existing structure and you place a landing on something that already exists, and then you're kind of doing your best in that scenario. And so the code officials would be fairly flexible about that. But if you were building an all brand new stair, in that scenario, there would be no reason to not make those the same riser height. And the code official would just be like, what are you doing? Why are you doing that? Like you're just creating a problem for yourself. But the fact that there can be differences, it's hard to answer because it would depend on all the other little pieces. In this scenario, I would say it should match.
Okay, and then Dustin is asking, what about the landing without the elevation? The riser height down 0 foot 0 could be different than a flight up to 810. I think that's the same.
Yeah, it's essentially the same question. And we could figure out what that is. I didn't give you enough information to figure out how high that is because I was trying to focus on the other issues. But if you had some length of run issues and some other things like that, you could calculate what height that was fairly simply.
And then last one here, Timothy is asking, why not divide 162 inches by 7 inches to get your 24 risers? Why did you do it in those 2 parts?
Because that's an important question, actually. I'm glad you asked that. And the reason for that is because if we did that, as we got up to the 810 height, the 810 was given to us because there's a floor there, and as we got up to there, it wouldn't be equal. It wouldn't the riser that was near there would not line up exactly with that floor plane. So we can't do it as a full run. It's possible in this case, when you did that, I think what you're saying is just mathematically, if we do it, we'll be reasonably close. But it's actually possible to get the wrong number because you can be, they can be very, very close from one to another. And when you divide overall, you'd get a different, it would be one off.
Okay.
One other quick thing to say about this, just this is sort of obvious, but I teach a lot and I've had a lot of students, and man, the number of times I've seen this as a silly mistake, so it's just worth saying. If you imagine that you have stairs and they're going up, let's say in this little case I have 1, 2, 3 risers. I have 3 risers, but I have one and 2 treads. People will make this mistake all the time, where they'll say, okay, there's X number of risers and they're at this height and the treads are at this. How long of a run of stairs is this? And people will multiply the number of risers times the tread width, forgetting to subtract one of them. So that's just a little side point to think about. All right, number 6. What is the steel thickness range for light gauge cold rolled metal framing? So this is when you're using metal studs, metal joists, that kind of thing. So it's not structural steel, which would be wide flanges and channels and things like that. This is those kind of very thin folded forms that make up the metal studs. And first thing to say is, rather oddly, I think oddly, the way that you refer to the thickness is through the idea of gauge. And the larger the number, actually the thinner the metal is. The smaller the number, the thicker the metal is. And so I find that sounds kind of backwards, so it always bothers me when I look at it. But as long as you kind of remember that, you'll be fine. And the answer here is that the range is actually A, 30 gauge to 8 gauge. So what this is talking about is 30 gauge is really thin metal. I always joke around about it on sites that's like folding tin foil and then hoping that it'll work as a stud. There are certain things that's going to be good enough for, and you might as well go with something that's thin and light if it's not necessary for it to be thicker and heavier. If you get down to an 8 gauge, like I actually have never even used an 8 gauge. I think the thickest I've ever used on any of my projects is probably a 12 gauge, I think, maybe a 10 gauge. That's actually pretty thick. It's not as thick as a structural steel member, but it's actually getting pretty solid. And so the range here is, there's going to be a huge number of times when you're doing an interior layout change, there's a simple partition, and it's just sort of between the floor and the ceiling and doesn't really carry anything other than the drywall. That might be a 24 gauge or something along those lines. Like pretty light scale, cheaper, easier to carry around, doesn't take as much gas on the truck to carry it from one place to another. It's very, very lightweight and very easy and does the job just fine. Kind of intriguingly, it actually uses the drywall as part of its structure, which is a little weird, but that's how it gains its stiffness. But if I'm doing something where it's actually a load-bearing wall or it's a stiffener for the overall structural setup, I'm definitely going to want to have something that's going to be thicker than that, something that's going to have a little bit more robust of a capacity. And so that's when I'm going to get down closer to 16, 14, 12. And really, when I start getting into like actual, really bearing walls, I'm really talking about 12s and 10s and that kind of range. And I guess 8s. Like I say, I've never actually used one, but that would be the range of how these things go. It's very, very rough justice. It's not actually accurate, so don't take this as gospel or anything. But you can kind of think of the sizes as a 30 gauge is sort of roughly 1/30th of an inch, and an 8 gauge would be roughly 1/8 of an inch, although it's actually thinner than that. But it just kind of gives you kind of a rough idea of the kind of range that we're talking about. And obviously when you look at that, that's a lot different, right? Those are, that's a lot of steel, a lot of weight, a lot of cost difference. And also, clearly if I started putting any reasonable heavy load on a 30 or 24 gauge steel, it's going to buckle. If I start doing it on one of these thicker ones, like a 12 or a 10, the material itself is thick enough that it's going to get much harder for it to buckle. And then the other thing that makes it not buckle is that it's folded into a shape, right? That the strength actually comes from the folds, right? So it's going to look something like that. Let's see there, how's that for? Yeah, that's about right. The sheer fact that this is cold rolled means that it's been recycled, usually, not always, but I think something like 92% or something like that of these things are recycled old car parts. Be interesting to see what happens as their cars get more and more plastic, where we're going to get our steel studs from. But they're generally old recycled pieces that get heated up, melted down, laid flat into giant sheets, cut with stampers, and then folded. And the fact of the folding actually gives it strength. And that's why it has these double folds. And then they stamp out holes so that there's the ability to have pipes go through without having to drill anything. The studs are like that. The bottoms, the runners, are actually going to look more without the second fold. It's just going to be the one fold. And that's so that these can fit in between, and then you can screw them together into the runner. So they lay the runners down, and then you fit these things in, and then you add the drywall, and it all starts very flimsy, and by the time you have it all together, it's actually pretty darn solid. So it's kind of an amazing, very simple, very engineered down process. The fact that it's cold rolled really refers to sort of the specifics of the way that it's made, but also has structural implication. A hot rolled would be more of a structural steel situation, and that structural steel is going to be thicker materials, and the only real way that you can easily do it on mass scale is by doing it hot rolled, and you're getting these much more complicated shapes, and that's going to be beneficial to the ductility of that steel. This is going to be less ductile. The reason it gets its ductility is just because it's thin, but you're trying to make it as stiff as possible out of a very thin amount of material. So you're using the structural capacity of the cold versus the hot, and the folds versus the shapes. You're finding the ways that those different structural capacities are actually helpful to the specific task at hand. Hope that made sense. All right. Quick question here.
We do have a couple of questions here. So Michael was asking, is this differentiating LGMF from framing studs, Division 5 versus Division 9 studs?
Yeah, all of those together would be in the 30 to the 8 range. It's kind of putting them all in one thing.
Okay, and then Jordan is asking, can you leave it to the contractor in the general requirements of a CD set, for interior partition walls, for example?
It depends on the kind of thing you're doing. If you're talking about interior partitions, like most buildings, if you're working in a bigger building, a bigger office building, there's probably like a set way that they do it. So they'll just go with that set way. And that's you don't really need a structural engineer or anything like that to figure that out. But I was actually just today at doing a walkthrough with a friend of mine who has a new kitchen structure, and it's in a bigger building, and they were talking about how the landlord developer went in and put in a demising wall using 16 gauge studs, and that kind of makes sense in the world of demising walls, and that was great until they realized that they were actually doing a mezzanine, and they were going to be using that wall as a structural wall, at which point they had to be 12s, and there was a whole discussion that the landlord hadn't looked at the drawings, and the architects had put 12s in the drawings because they knew the mezzanine was coming, but the landlord was just kind of doing the thing they always do and put in the 16s, and it didn't meet the structural capacity that they needed to be able to hold the floor up, because it wasn't just a partition anymore, even though it was a fire-rated partition. It wasn't just a fire-rated partition, it was also a structural wall. So that's the trouble with letting just kind of the folks do what they always do, is that if you don't think it through at least, you may find that there are spots where that's just not true, and you really do need to be very careful about which elements need to be in these thicker, more robust ranges. All right, number 7. So I often will talk about, because I think this shows up on the exams a lot, kind of interesting words. Some of you may have heard me say the Virendeel Truss, for example. Like, it's sort of a thing that doesn't show up a lot, but it's an interesting word, and so it shows up on the exam a lot. Well, here's one, Pozzolans and Superplasticizers. These are just great words, and they're easy to ask questions about. I don't know what kind of questions they would ask, but I just thought we'd sort of use it as a way to kind of get into some of these issues. So, question 7, Pozzolans are added to concrete mix for. This actually has 2 potential answers, but the first one that I would answer is that they are added for strength. What they're really added for, though, when you kind of look behind the scenes, is actually to save money. Because what Pozzolans are generally, there's quite a wide range of Pozzolans. They actually, the term actually comes from the Roman days. It has something to do with lime or something. Back in the Roman days, and so it's a term that has been around for literally thousands of years in different, quite subtle variations. But these days, when we talk about Pozzolans, we're usually talking about things that are similar to fly ash or something like that, and those are industrial products that are kind of offshoots from when they're making something else. And there's a bunch of examples of it, of these things that are nobody wants. And so if we can use those, and they will do a similar thing to what the Portland cement does in the concrete, where it hydrates and mixes in a sort of chemical reaction in order to create a strong bond that then holds the aggregate in, at first a paste and then eventually a very solid structural wall. If we can do that, the Portland cement is very expensive, so if we can take some of the Portland cement out and put in some of this material that we can essentially get for free, it can reduce the cost of the wall, it can be helpful, but it also is keeping the strength or giving a different kind of version of the strength into that concrete wall. So strength, but really the background of it is that you're trying to save money by using these industrial cast-offs. And then superplasticizers are a very different animal. Sometimes it'll be just referred to as plasticizers, sometimes superplasticizers. There's a few other terms for these things. This is the reason that you would add that to a mix is for workability. And what we're talking about there, workability, oh, there we go. There's an I in there as well. What we're talking about there is, like, let's say you're the guy on the job site and a concrete truck shows up and you have to add a little bit of water at the end, and it's to get the mix just right. And it's 4 o'clock on a Friday and you really want to get home, and there's a lot of complicated form work and a lot of rebar in there. Like, what you really want to do is you want to make that concrete really wet. You want to add a bunch of water to it. So you're going to put a bunch of water into the mix. So you've got Portland cement, you got the aggregate, you got a couple of other things, and you got the water. And the water and the Portland cement are going to have a chemical moment with each other, and they're going to produce heat, and they're going to produce this kind of crazy reaction that turns it into a solid, the thing that we think of as concrete, that solidness. And by having it be sort of pasty, the pastiness of it, the sort of flowing pastiness of it, allows for the aggregate, the big chunks of rocks, to be suspended in that paste, which is what you want. But the more of a hard paste it is, the harder it's going to be to fit in around all of the rebar and in complicated formwork. So imagine I have a wall and I've got a bunch of rebar down at the, somewhere in that wall, and I'm trying to place this concrete in, and I'm trying to get it around all that stuff. The more workable it is, the more wet it is, the more water I put in, it's going to make that way, way easier to kind of fill in, and it'll just, be like, kind of water kind of filling in around all those things, which is going to be awesome if you're the guy trying to get there and get out and get home to your family. But the wetter it is, the more soupy it is, the less that the aggregate will remain suspended in that mix, and so you'll start getting all the aggregate falling by gravity down to the bottom and all the cement rising to the top, and that's going to be a terrible wall. So you don't want a really, really wet mix of concrete for that reason. But the other reason you don't want that is that there's actually a very limited amount of the water is needed for this chemical moment with the Portland cement. That chemical moment actually only really needs less water to go through that chemical process than what you need to make it workable. So there's already, even in the stiffest concrete paste that you're using, there's already too much water. So the more water I put in there, I'm actually making the concrete weaker and weaker because I have all this excess moisture in there that then has to get out, and it leaves void spaces, and it causes all kinds of problems. So if I am looking for strength, I want to go with the least amount of water I can get in, I can manage to use, because I want to make it as close to the right amount of water per amount of cement, so that you have just enough that really makes all the cement work, and then as little extra as possible. But if I do that, it's like not workable at all. So it's maybe possible to do something with a very, very stiff paste if I'm doing it for a precast structure where I have a lot more control over how the formwork works. But if I'm out on a job site, I have to have more workability than that. So, okay, how do you do that without reducing the quality of the concrete? Well, one of the ways you can do it is you use these Superplasticizers. And what they do is they just kind of, it's almost like giving like a little bit of, it makes everything feel like it's got a little bit of wax on it. It doesn't have anything to do with wax, but you start to get this situation where all this stuff is moving back and forth much more flowy and easily. And it'll do that for a little while as if you put more water in, but then after about 30 minutes, it'll speed up and cure very, very quickly, and then it'll go on to the sort of normal curing process. So it's a way of keeping the strength of the concrete, the compressive strength of the concrete, but getting it to be much, much more workable. Also, like I said, I just love those words, Pozzolans and Superplasticizers. So it's just an easy one to talk about. All right, here's a simple one. We're on to number 8. How many board feet are there, I guess, in a 2x6 joist measuring 12 feet long? So if you haven't heard the term board feet, you should definitely sort of get a handle on it. It's a very simple idea, but for some reason, they always seem to ask questions about board feet. The reason that you would actually never ask a question like this in real life, because you wouldn't talk about a 2x6 that's 12 feet long in board feet. You would use it if you were buying a trainload of wood for a housing development or something like that. You would say, well, how many board feet is in each car? You know, it's a way of buying large quantities of wood, of usually dimensional lumber, but it can be other things as well. So one board foot is 1 inch deep by 12 by 12. So that's a board foot. And we're using nominal dimensions, not actual dimensions, nominal dimensions. So a 2x6 that's 12 feet long, there's a couple ways. I just do it graphically from in my head, and I'll just draw it out for you. So I just start as I imagine cutting it in half in this case, because I happen to know that a 2x6 sitting next to a 2x6 is going to be 12, right? Damn. So I have one, and then I have another one right next to it. And what that is giving me is I have a 6-foot dimension, I have a 12-inch dimension, and I have a 2-inch dimension. And so if I think of that as 2 layers of board feet, I have the 12-inch dimension, and I have 2 layers of it by 6. So I have essentially 12 board feet. So the answer is going to be B, 12 board feet. This is a very simple version. You can imagine you could get a question that's like, okay, you've got 300 2x4s and 150 2x6, you know, something sort of dopey like that. And you just have to kind of find, the reason I do this graphically is that when you do that, you just kind of find a sort of, all right, 2x4s, I line 3 of them up next to each other, that's 12 inches. So then I can stack 10 tall, and I can very, very quickly come up with how many board feet that is, and just doing it in your head kind of graphically. But for some reason, this shows up all the time. So there you go, board feet. Now you feel comfortable going out and buying trainloads of wood.
Looks like everybody got that one.
Cool. Number 9, which of the following cuts from the same log would produce the flooring with the best wearing characteristics? Quarter sawn, plain sawn, rotary sawn, half round sawn. I've done a little bit of this in some other locations, so you may, there's a longer discussion of it in some other spots, but I think this is kind of a nice one because it touches on a bunch of issues. So let's say this is our log, and there's a log. The answer to this is going to be quarter sawn. So I'm going to talk about quarter sawn for a second. Quarter sawn, if you imagine you're cutting that log into those quarters. And then once I cut those into the quarters, I'm going to cut my boards out in that sort of awkward way like that. And you can tell immediately that I start getting with all these little weird triangular little leftover bits of space. So this is not an efficient way to cut a log. I'm going to end up with lots of extra bits. Now these days all that extra bits goes into something, goes into OSB or particle board or something. So it's not like it gets totally lost, but it's not highest and best use. So it better be a good reason to do the quarter sawn because you're losing a lot of what would otherwise be revenue producing. So the reason for that is that if you imagine any one of those pieces, so let's say we're talking about like this one right there, the rings of the tree are essentially going right like that. So the rings are going roughly straight across. So if we then think about it as a board of wood with those little things, I'm going to see the grain on that front face essentially vertical. So the rings are hard rings that are the darker ones, and then lighter rings which are the softer ones. By having that board with that fairly even spacing and that vertical line, that means all the hard and the soft are balanced, and so the hard is going to be protective of the soft, and it's going to wear much, much better than any of the other kinds of wood flooring that you might get. So let's talk about plane sawing for a second. So if I have that same situation with the plane sawing, there's my log. In plane sawing, I'm not going to go to this thing of where I'm going to cut it into quarters or anything like that. I'm just going to start finding these lines across. I'm going to cut it into those. It's going to be the most efficient way to get as many boards as I can out of it. But a bunch of those boards are going to end up in situations where I'm going to have something like the grain doing something like that, right? Where I don't have it going straight across effectively. I have it in some awkward other way. So when I do the look at the side at this main run, you'll start seeing what's referred to as cathedraling, where you'll start getting those kind of awkward amounts, these big flat areas of soft parts with then the little kind of bits of the hard rings. And when you walk on that, it's going to wear very, very differently than it would if you were walking on a quarter sawn. Now, some people really like that. There's times when it's appropriate. It's often referred to as character wood. You'll find that people will do it on purpose for kind of a cabin look or something like that. So it's not necessarily bad, it's just different. And since the question was asking about wearing characteristics, you want something that's going to wear evenly and consistently. So quarter sawn, plain sawn, rotary sawn, and half round sawn, those are really for other kinds of plies of things, plywoods and veneers and a bunch of other stuff like that. All right, number 10. Increasing the carbon content in steel has what effect? Does it make the steel more flexible, make the steel less ductile, make steel more corrosion resistant, make the steel easier to weld? This is one of the examples where there's actually a couple of right answers, but one is probably a better right answer than another. A is definitely not true. Adding carbon into steel does not make it more flexible. And D is definitely not true, making it easier to weld. Those are definitely not true. The two that are sort of pretty reasonable answers are B and C, but the best answer really is C. Because that's the reason that you have, that's one of the main reasons why you have these differences. So just a quick kind of backdrop onto all of this. When kind of construction steel really first started happening, it wasn't steel, it was actually cast iron. And so cast iron was this kind of miracle material that people, at first were using for tools and for like swords, and I'm not sure if they use cast for swords. I don't think it would be a good sword, but they use it for very specific kinds of tools, and it was very interesting, but it was hard to make, and so you'd make relatively small amounts. Then they started figuring out how to make much bigger amounts, and they started using it for structural purposes. A number of disasters later, they realized, wait, we've got a problem here. And that problem was that the material is very, very strong, but it's also very brittle. And that material has kind of in the range of, I think maybe 2% to 5% or something. 5% sounds like a lot, but I think I've seen that written, of carbon in there. So all that carbon makes it, helps make it strong, but also makes it very, very brittle. So by reducing that carbon, we're able to make it much more ductile, which is really helpful. It makes it easier to weld. It does all kinds of these really strong benefits. And so typical mild steel is probably going to be something like 0.3%, so it's way less. As you get into like higher content carbon steels, you might get up to like 0.5%, maybe even a little bit higher than that, probably less than 1%, definitely less than 2%. And those ones have certain benefits, but as you get up to those larger numbers, you're going to start losing some of the ductility. You're going to have certain disadvantages of it. The ductility is really important because the ductility means that flexibleness, that the steel, when it gets loaded, it can flex, but then when the load is taken off, it goes back to its original shape. It's incredibly helpful for buildings. And one of the big advantages of it is that if things are really going terrible, it will bend before it finally gives way. So if you're a firefighter running through a building or something like that, and you feel the floor is actually bending below you, you know it's time to get the heck out of that building. So it's an incredibly useful aspect to how steel works. But by adding a little bit more of the carbon, we're making it a little stiffer, and that way it's not as ductile. But also, the reason that you would really want that is it does these other things. For example, it's much less open to certain kinds of corrosion. And so depending on where you're using it, it has these certain advantages. All right, I'm going to jump on, so we're getting a little late here. Number 11. This is actually a very simple one. Which of the following is the most characteristic of an end-bearing foundation element? So all of these, the timber piling, the belled caisson, steel micropiles, tapered precast concrete piles, those are all large-scale foundation systems. Actually, micropiles are not necessarily large-scale. They can be large-scale. But those are for systems where you're going down pretty deep into the ground. But they also act very differently, and the key thing on the question is end-bearing. Timber piling, generally I'm going to find there's going to be a bunch of these that I'm going to put together, and they're going to go very deep into the ground. So there's my ground plane. I'm going to group them together with like a little concrete pad on the top so they act like one. And I'm going to not really worry, like when they go down into the bottom, I'm not really trying to get those timber pilings to actually stand on anything. These are essentially telephone poles. Like they're long straight trees that have been trimmed down, and I push them down into the ground. And just in the same way that if you're out walking around like along a beach or something, or near some mud, and you have a stick in your hand, you stick the stick into the mud and you try to pull it out. Sometimes it's hard to pull out. That's the friction that's happening between the stick and the mud. Well, the piles are doing exactly the same thing, just the other way. So I'm not counting on these piles as end-bearing, although there are some very specific times when that happens. But most of the time when I'm talking about piles, I'm really talking about friction-bearing. So it's just the fact that these things are pushing against the soil in various ways, and it's creating this sort of cloud of friction around it, and that's how you can actually, there's a technical way to sort of add up that amount of friction, and you can decide how much load you can put on those piles, that group of piles, in order to hold up your section of the building there. So the piles are happening through a friction fit, not through end bearing. The micropiles are similar. They're kind of a coiled system. The tapered piles can go either way, actually, but the one that really speaks to end bearing is the belled caisson. So in the belled caisson, we've got a situation where we've got our ground plane, and we dig down, and as we dig down, we actually literally bell it out down at the bottom. And so that would end up, we'd dig it out, and we'd end up filling it with concrete and rebar. And the way they do that is they have this auger system that comes down, and it has a blade that can fall down and out. And as that auger spins around, they don't let it fall until it gets to the level they want, and then you bell it out and make it much bigger down at the bottom. And the whole idea here is that I've got some bedrock down here, and I have a really high capacity PSF of the bedrock. Let's say it's, I don't know, make up a number here, 12,000 PSF down there. This maybe is, let's say, 80 feet down. And all of this soil, which is much less capacity than that bedrock, I'm essentially just going to ignore all of this. This is like building a column on top of the bedrock that goes up through 80 feet of air. Now it's kind of handy because it's braced because of this soil, but I'm not counting on any of that soil for the structural load. I'm literally just building a column all the way down to this very suitable soil of the bedrock. And because that's what I'm doing, and because I want to get as much, I'm going way down in order to do this. I'm going this 80 feet or 100 feet or 110 feet. I've seen up to 200 feet. I know sometimes these are shorter, like 30 or 25 feet or something, but generally when you're talking about caissons, you're talking about 50, 80, 100, 110 something feet. So you're going a really long way. Well, I don't want to do that and then have an end-bearing thing that's just a few square feet. I want it to get as much of that capacity as possible so I can carry as much load for the building as possible. So the bell, which is this little shape here, is the belled caisson, and that's absolutely would be the answer. So B would be the answer on this one. Okay, let's move on. One last one here. 12, standing at the job site, watching the concrete coming out of the truck, I'm worried about the concrete being too runny or wet. Which test should I consider? So we have the vane shear test, the cylinder test, the slump test, and the ACT test. Well, first off, you should recognize the ACT test is the test that high schoolers do, I believe. So that's not the right one. So it's definitely not D. So then we have these other three. A vane shear test is actually a soils test, and that's one when I've got this little device that kind of fits in the ground. This is not a great drawing of it, but I think you get the idea, and it has a little handle on it. And you stick it down into the ground, and then you turn it. You try to make it go around. And what that's going to do is going to tell you what kind of soil it is. Like if it's a running soil, like if you can twist it easily, that means you're not going to get any horizontal capacity, anything that's going to stop your building from shifting horizontally if there's an earthquake or if there's some other or hydrostatic issues that are going to push things one way or the other. So it's going to tell you what kind of soil that is, and it's a very useful thing to know in very specific situations, especially ones that are kind of have to do with retaining. But that's about soils. It's not about concrete at all. So that definitely is not it. So it's not A and it's not D. So we can definitely rule those guys out. So then the question is it B or C, cylinder test or slump test? So cylinder test, fairly straightforward. I have somebody is pouring concrete, and as they're pouring concrete out of the truck, you're going to, off to the side, you're going to have a little formwork that's a cylinder shape, and they're going to pour a whole series of these little cylinders that are usually 12 inches tall. I think they're 6 inches in diameter, but I actually don't remember exactly. And you're going to make these cylinders, and you're going to make a bunch of them out of every truckload of concrete that comes. And then you're going to mark on it what the truck was, what delivery number it was, which batch of concrete it was, and then where that batch was being placed into the building. And you're going to make these little formwork pieces. You're going to put them into a storage area, and then you're going to let them cure, and then you're just going to let them sit there. And the reason that you're doing that is that you can then, at various points, say at the 7-day mark, maybe the 14-day mark, but definitely at the 28-day mark. 28 days is sort of the amount of time it's considered that concrete has fully cured. It actually technically doesn't cure fully until forever. It'll just keep curing, but it's so close to, like, the way the curve works. At 28 days, you're very, very close to that. So it's just a sort of a workable number that makes makes it easy to kind of, it's 4 weeks from now, that's when it's cured. And so the idea here is that this concrete is the same concrete that got put into the building. You have a whole bunch of these. They're all labeled very carefully. And then at some point, there's a worry, there's a reason to think about it. You come into a device that smashes it, a big hydraulic press that presses in and checks the compressive capacity of that cylinder of concrete. And then by using the very particularly calibrated system, they can figure out what the capacity of the concrete was. And then you can say, yeah, that was what we ordered. We said we wanted 7,000 PSI concrete, and it came out to 7,000, or it came out to 7,500 or something. So that works just fine. Everything's good. You probably don't end up crushing them all. You probably just do ones along the way to kind of check to make sure everything's okay. Or if there was a problem, maybe you were very carefully organizing these things and then you're crushing them right away, and you're going to check the one at 7 days, you're going to check one at 14 days because people are worried that there was a problem and you really want to check it out. But for a lot of the time, they would make these, do a few sample tests, because it actually costs money to crush these things. So you're probably not going to crush them all the time. And if you're doing a smaller project like a house or something, like a single family house, you're probably not even going to do the cylinders. But for any larger project, you absolutely should. It's probably part of the contracts, and it allows everybody to sort of check it out. But this is something, like, if you're figuring out at 28 days that the concrete was bad that they put in, it's kind of too late. It's already after it's been done, and the problem is already done. It's already in there. So in the example that we're talking about here, he's looking at the thing, it's coming out of the concrete truck, and it looks too runny or wet. Like, if we claimed that the cylinder test was the thing to do here, that means we wouldn't figure it out until a month later. Well, that's not terribly helpful. That means you got to go back in. This is a month of construction that has kept on going. You have to go back in and rip it out if it's a problem. It's a big, big, big mess. So the actual answer on this is, of course, the slump test. And what that is I have this truncated cone, which is like a big cup. I fill it with the concrete. I then flip it over, and I make that cone go the other direction. I take the cup off, this truncated cone off, and I see how much that shape slumps down. Literally, it's a slump test. I'm measuring the slump. And if I end up with a situation where it slumps down into like a little puddle, well, that's way too much water in that mix, and that's going to be a terrible, terrible concrete mix. If I take the cone off and it doesn't slump at all, it has a zero slump, it stays exactly in that same form, well, that might be useful for precast, but it's going to be almost impossible to use out on a job site in any complicated formwork or trying to get around the rebar and anything like that. So it's different for precast in a factory versus doing something on a job site. But typically what you're going to end up with is it's going to slump down, it's going to kind of go something, and you'll get somewhere in this kind of 3-inch range, maybe 4-inch range of slump. If for some reason you really don't need the compressive strength and there's reasons why you want it, you might even go as much as like 5-inch or something if you were on a job site and the slump was only like 1 inch or something, you might be able to get away with that in a simple scenario, but the vast majority of the time it's going to be something like a 3-inch slump. So that would tell you they do the slump test right there and then. If you get the puddle, you say to them, well, you don't say to them, but you say to the GC, hey, this isn't going to meet the thing. You guys should really not put this in because we're going to test all these cylinders, and they would know to stop the truck, send it back, get a new truck in that has a better mix, a better slump, and would be more effective. So that's the 12 questions, and I hope that what you're seeing is, as we're talking about these very specific elements, what we're really talking about is kind of these big ideas of water, workability, the process of how these things go, kind of means and methods, keeping things to be structurally sound, and those things end up being shown and the questions end up being asked through these very minute pieces, but in fact they're talking about these bigger issues.
All right, so we've got a couple of good questions here. At this point, we'll open it up for a few questions. And so we'll start with Allison's question. She goes back to the stair vignette. And she says, when we do the stair vignette, does the same riser method apply where the risers are different sizes?
Yes, I can almost guarantee you that there will be 2 different risers on the stair vignette because they want to just check to see if you get it. They will in fact do that. And that happens all the time. You will find it's actually pretty rare if you have 3 heights or more, that everything will work out perfectly. The first floor to the second floor is probably a different riser than the second floor to the third floor. If you have a building that has a lot of very similar repetition floors, you might have all the same from like the 3rd to 4 and 4 to 5 and 5 to 6 might all be the same riser height, but that first to second is likely to be different for exactly the reasons that we talked about.
Okay, another question here from Devon is asking, what advice can you give in the understanding of the effects of attaching dissimilar elements to concrete?
Oh man, that's a big long question. It's a really good question, but it's a big long question. Specific metals will actually dissolve in concrete. And so you have to be very, very particular about it. I kind of don't want to get too deep into it right now because I don't want to say the wrong thing, and I should really sort of make sure I've checked up recently. But absolutely, this is actually true both from metal to metal and from concrete to metal. There are situations where if I use a screw of one type and a washer of another, they will have a electrolyte reaction with each other, and one will corrode and it'll actually tear itself and dissolve essentially. And so you have to be very careful about metal to metal, but the same situation can happen with the concrete and metals. Another thing with concrete that you have to be very careful of, those of you who have done like a platform construction, you may have noticed that at the top of the foundation wall, before you put the sill plate down, they should always, they don't always, but they should always put a sill sealer down first, which is like a thin layer of kind of squishy squishy material that stops moisture from penetrating through. And even if you're using pressure treated wood, the concrete, like I said, there's more water in the concrete in order to make it workable than it actually needs. And so the concrete will give off actually a shocking amount of water over a span of time, especially for the first year, that it'll just keep giving off water. And it will rot out any wood that's right up against it. So you have to find ways to separate these things. So you'll often see like these kind of fibrous elements, neoprene elements, things like that become separators between something that is being attached to the concrete, either if it's metal or wood. But you should absolutely look up the specifics of which kinds of metals can touch the concrete, because a lot of them can't. This is also one of the reasons why you have coatings on a lot of the rebar and things, is that you get the salts that go in with the waters and stuff like that, and you need to have coatings on there to protect that metal.
Allison is asking, what is the ACT test again?
I was joking on that one. Sorry, I should be careful. That was a high school test for like English or physics or something, just to throw you off.
Michael was asking, do you know how many questions you can expect on this part of the exam?
Yeah. So okay, one question, which is a similar question, which I often get, is, all right, how many questions do I need to answer correctly? And I always try to dissuade people from even thinking or worrying about it. The number of questions, I forget, I should have looked it up, but it's something like 85 or something like that. It's around 100, a little less than that, for an exam like this. But that doesn't mean that those all are questions that are going to grade for or against you. It's quite possible that they may have realized that, I'll give you an example. A few years ago, about 2007 or so, I was teaching classes on this stuff, and people talk to me all the time about this, as you might imagine. And so they came back and they said, "Oh my God, I took the exam after we did the class, and like there were like 30 questions on sustainability. Like what was up with that? We barely talked about it. And what had happened in that scenario was that NCARB had kind of realized that they were behind the curve on people talking about sustainability. And in 2002, very few people were really deep into thinking about it. But by 2007, 2008, if you weren't thinking about sustainability, you weren't talking about architecture. Like it had become very much a part of the discussion. And they realized they needed a lot of sustainability questions, but they didn't have a lot of them already written. So they wrote a whole bunch of them and then put them into all the different exams. And then as they would go through it, they would check out. If they put a question in that 100% of the people got it right, well, that question's too easy. And so they would throw it out, or they'd throw it out for you and then rewrite it into a different situation and put it back in. If 20% of the people got it right, well, that's too hard. They'd throw it out. So there's often test questions in there. In that case, there was a whole lot of test questions going on. In any scenario, there's always going to be a few test questions, and you just don't know which ones are actually counting for, are actually part of your actual exam, and which ones you're just answering test questions for them to understand. Do people understand the question? Does the wording work? Does, even if it is a reasonable question, was it just too hard? So I wouldn't worry too much about it. The question run will be somewhere about 75 or 80 that count for you, but don't worry about it. Just answer the best you can.
So we'll take two more questions here. Dustin asks, when you get a submittal for a concrete mix design, they include a compressive strength test history for that mix design.
Yeah.
The plant provides that, but where does the testing history come from? Is it from cylinder tests used on previous batches, for example, other projects, or not?
It actually can come from two different sources. One of them is that on bigger, more important buildings, you can imagine this stuff is watched very, very closely. Like if you're doing a bigger building and the compressive strength of the concrete is vitally important to a multi-floor structural situation, you're going to be very careful about checking these. You're not going to crush all of these cylinders, but you're going to check a lot of them. And the different mixes, if they find that they do a mix and they crush them and they always get back a really consistent number, then that's something that they would take that information back and they would use that in their documentation. But often they'll have their own systems of, like the cylinder test. You actually don't go back typically. I think you do some places because there's just not enough resources out in certain parts of the country. But in the best case scenario, you wouldn't take the cylinder back to the place you bought the concrete from. You would take it to a third party, because what you want is somebody else to look at it for you. So there's somebody who's not interested, and they may not even know what the concrete mix was supposed to, what compressive strength it was supposed to get to. You actually don't want them to know. You want them just to do the test, and they say, yes, it came out to 7,200 PSI or 3,000 PSI or whatever it is. So if they're doing that, they're probably using their own testing as they came up with the mix. They've tested it and tested it and tested it, kind of perfect the mix, and then they'll settle on one. And so they've been testing it for themselves, but then they would be able to also check, because they would look at the logs of other people's tests and make sure that their numbers were the same as the other people's numbers. So it'll actually be both. And it's partly, I'm sure, dependent on which company and which location.
Okay, and then finally here from Tom, he wants to know if is board feet the same for actual or nominal dimensions?
You can actually, you must use nominal dimensions, because like when I was doing this really simple one, it's obviously the same, because there's only one board and like it ended up being very similar. But you can imagine that if the difference between something that's 1.5 inches tall and something that's 2 inches tall in terms of how you start adding it up, if I am thinking of this as like a train load, that's a giant amount difference. And so you would be way, way, way off if you were using the actual. So it's definitely the nominal dimensions that are used for board feet.
All right, well, we'll end it there. So thank you, Mike. And thanks to all of you who've tuned in, and to Devon, Dustin, Joshua, Judd, Kevin, Michael, and Jerry, who submitted their answers to the questions.
Yes, well done, guys.
Yeah, if you guys would like to attend our next ARE live broadcast on the schematic design exam, Visit blackspectacles.com/podcast to register to attend. Just like today's episode, you'll have a chance to ask questions and share your answers with Mike for live feedback during the broadcast.
And that one's really different because it's about the vignettes and it has a very different flow to it. So it'll be similar, but quite different discussion.
And you guys should know that ARE Live is now a podcast. So if you go to blackspectacles.com/podcast, you can actually you can subscribe to the podcast via iTunes or Stitcher, or you can watch any of these video replays on our YouTube channel, which you can get to also from that podcast page. So you can take ARE Live with you in your phone or your any device. So you can have Mike in your ear.
So now you can ruin your vacation anywhere.
Yeah,
there you go.
Right. And then also, of course, to learn more about our AIA ARE prep curriculum, go to blackspectacles.com, where you can prepare for the ARE in all 7 sections of the exam, including the one we covered tonight. We'll put a link in the show notes. And for those of you who want to get busy preparing for the ARE, if you're already an AIA member, you can visit aia.org/ARE prep to get a 15% discount for the entire duration of your AIA ARE prep membership. Finally, please leave a comment below the video to let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.